Somewhere out there, right now, there could be a rock tumbling through space that looks like a dice. Sharp edges, flat faces, perfect 90-degree corners. It's not science fiction. Small rocks like that exist by the thousands, drifting between Mars and Jupiter, spinning end over end like a thrown stone that never lands. So here's the question that sounds almost childish until you actually try to answer it. If a rock can be shaped like a cube, why can't a planet? Why does every single planet we have ever found in our solar system and in thousands of others always end up round? Not oval, not boxy, not a pyramid, not a cube, not a strange crystal shape. Round. Every time. And the answer to that question is not really about geometry. It's about a fight. A fight that every massive object in the universe eventually loses, whether it wants to or not. Think about how strange that actually is once you sit with it for a second. We live on a planet covered in straight lines, skyscrapers with 90-degree corners, bridges built from flat steel beams, entire cities laid out in perfect grids. Humans build square things constantly because square shapes are efficient, stackable, and easy to engineer. So why does nature, when left completely alone with unlimited time and unlimited material, never once choose to build a planet the same way? Why does every star, every major moon, every planet in every solar system astronomers have ever pointed a telescope at, always come out looking like a ball? If square shapes were just as valid an option, surely somewhere in the billions of planets scattered across our galaxy, at least one of them would have kept its corners. And yet, not a single one ever has. That's not a coincidence. That's a law. Let's start with the obvious thought, the one almost everyone has the first time this question comes up. A square planet sounds possible, right? After all, we build square things constantly. Buildings, boxes, bricks, even dice are cut into perfect cubes, and they sit there just fine on a table. Mountains have flattish faces and sharp ridge lines. Crystals form with razor-straight edges all the time, sometimes growing for miles underground in huge geometric shapes. So if a crystal can have 8 corners and 6 faces, why couldn't a planet, given enough rock, just keep that same shape as it grows bigger and bigger? It feels like nothing more than a matter of construction. Stack enough material in a cube pattern, let it settle, and you'd have yourself a cube world. At small scales, this isn't even wrong. Tiny objects in space genuinely do hold weird shapes, sometimes for billions of years. The problem isn't the idea of a square shape itself. The problem is what happens the instant that square object starts getting big. Picture, just for a moment, that someone actually managed to build a planet-sized cube. 6 perfectly flat faces, 8 sharp corners, sitting in space the way a 6-sided die sits on a table. Now press play and watch what happens in the following days. The corners begin to sag. Not crack, not explode, just slowly droop downward like wax dripping from a candle that's been lit too long. The flat faces start to bulge outward in the middle, the way a thin sheet of plastic bows out when you push on its center. Within a surprisingly short amount of time, on a planetary timescale anyway, that crisp cube has softened into something lumpy, something closer to a poorly shaped potato than a die. Keep watching, and within a few 100,000 years, even that lumpy shape smooths itself further. The cube never had a chance to stay a cube. The moment it existed at planetary size, it began erasing its own corners, like a sandcastle left too close to the surf. Except the tide attacking it wasn't water. It was its own weight, pulling itself apart and rebuilding itself into a ball. So where would all of that material from the corners actually go? Here's something that sounds backwards at first. The corners of a cube planet wouldn't be small or unimportant. They'd be the single tallest, most violent geological features anywhere on that world. The kind of mountains that would make Mount Everest look like a speed bump. Think about the geometry for a second. On a sphere, Every point on the surface sits at roughly the same distance from the center. But on a cube, the corners stick out dramatically farther from the center than the middle of each flat face does. For a planet-sized cube, that difference could be hundreds, even thousands of kilometers of extra rock sticking out into space at each corner. An alpine spike taller than anything biology or geology has ever produced on a normal world. And a mountain that size, sitting on top of that much extra mass, has only one possible job ahead of it under planetary gravity: collapsing under its own weight, hour by hour, year by year, until it isn't a peak anymore, but a gentle curve blending back into the rest of the surface. That collapse happens because gravity does not treat every part of a planet equally. Gravity always pulls toward the center of mass, the rough middle point of all that material. On a perfect sphere, every chunk of surface rock is the same distance from that center, so the pulling force lines up neatly, pointing straight down relative to the ground beneath your feet, everywhere you'd stand. On a cube, the corners are the farthest points from the center, which means they have the most material stacked up above a base that can't support it. Gravity finds that imbalance immediately and starts working on it, pulling down hardest exactly where the structure can least afford it. But here's what makes a cube planet even stranger to think about, something most people never consider until they try to actually imagine living on one. On a sphere like Earth, down always means the same thing no matter where you stand, toward the center of the planet, directly beneath your feet. Point your finger at the ground anywhere on Earth, and you're pointing, more or less, straight at the core. That consistency is what makes a round world feel normal and navigable. A cube planet would not offer you that. At the center of one of the flat faces, gravity would pull you fairly normally, straight down toward the planet's core, and you'd feel relatively at home. But the moment you started walking toward an edge, something deeply wrong would begin happening. Down would start to tilt. Not dramatically at first, just a slight diagonal lean, the way a floor feels wrong before you realize it's sloped. But keep walking, and that tilt would keep growing, degree by degree. By the time you reach the edge itself, gravity wouldn't feel like it was dragging you straight through the ground at all. It would feel like it was pulling you sideways, angling you back toward the middle of the face you just walked away from, because that's where the planet's bulk is more evenly centered beneath you. You'd be walking on what felt like flat ground, but your body would be leaning backward, as though the middle of the face were subtly calling you back. Reach the very corner, and the sensation would be stranger still. Gravity pulling you diagonally inward from 3 different faces at once, a tug of war with no clean winner. The concept of standing upright would become meaningless, because upright would point in a different direction every few kilometers, depending on where you happen to be. Walking in a straight line would feel like walking uphill in one direction and downhill in another, even across completely flat terrain, because the gravity under your feet would be quietly rotating the whole time. And this warping of gravity wouldn't just affect people trying to walk across the surface. It would completely reshape where water and air could even exist. On a sphere like Earth, gravity pulls every point of the surface inward with roughly equal force. So water settles into a single continuous ocean, finding the lowest available basin and filling it. On a cube planet, things would be far stranger, because the geometry creates 6 natural low points and 8 natural high points at the same time. Here is why. The corners of the cube stick out dramatically farther from the planet's center than the middles of the flat faces do. In gravitational terms, that means the corners are sitting at higher gravitational potential, the same way a ball at the top of a hill has more potential energy than one sitting in a valley. Water always flows toward lower gravitational potential. It doesn't flow toward wherever looks lowest to the eye. It flows toward wherever gravity pulls hardest. And on a cube planet, gravity pulls hardest toward the centers of each face, because those points sit closest to the overall center of mass. So a cube planet would not have one global ocean wrapped evenly around the world. It would have 6 separate oceans, one pooled in the middle of each flat face, each one isolated from the others by the elevated ridges running along every edge and the impossible highlands rising at every corner. The edges and corners would be the driest, most exposed terrain on the planet. Enormous natural highlands with no water, thin air, and a view across 3 faces at once. The center of each face would be a deep gravitational basin, flooded and atmospheric, sitting at the lowest point that water on that face could possibly reach. 6 separate worlds in one, separated not by mountains built from geology, but by mountains built from pure geometry. The atmosphere would follow the same pattern. Air would be thickest and most pressurized at the centers of the faces, where gravitational pull is deepest. Walk toward an edge or a corner, and the air would thin out the way it thins out as you climb a mountain. Not because you're physically ascending in any visible sense, but because you're moving to a region of higher gravitational potential, and the atmosphere simply doesn't extend as thickly there. The corners would be frigid, nearly airless, exposed to space in a way no mountaintop on Earth comes close to. And none of that would matter for long anyway, because those corners would be collapsing from the moment the planet existed. This leads to one of the most elegant ideas in all of planetary science. Somewhere between the size of a rock and the size of a planet, there is a threshold, an actual size where an object stops getting to choose its own shape. Below that threshold, an object can be cratered, lumpy, jagged, twisted into almost any shape collisions and chemistry give it, and it will simply stay that way indefinitely, because its own gravity is too feeble to do anything about it. Above that threshold, gravity becomes the dominant sculptor, stronger than the rigid strength of rock or ice, and from that point forward, the object has no real say in the matter anymore. Scientists have a name for this line: hydrostatic equilibrium, the point where a body's own gravity overcomes the rigid strength of its material and forces it into a rounded form. For icy bodies, this happens at a radius of around 200 kilometers, because ice is relatively soft and gives in early. For rockier material, the threshold sits higher, often several hundred kilometers in radius. But the outcome past that line is always the same. Shape stops being a personal feature of the object and becomes a mathematical inevitability, decided entirely by size. That threshold is exactly why asteroids get to stay ugly. Most asteroids, even surprisingly large ones, sit comfortably below that critical size, which means their own gravity is nowhere near strong enough to fight back against the rigid strength of their rock. That's why you see asteroids shaped like potatoes, like dog bones, like lumpy peanuts, like jagged stones thrown by some cosmic hand. An asteroid doesn't fight gravity and win. It simply never gets challenged to that fight in the first place, because it never crossed into the weight class where gravity starts taking shape seriously. But cross that size threshold, even by a little, and the personality of an object changes completely. You start finding what planetary scientists sometimes call potato worlds, objects sitting right at that uncomfortable in-between zone, big enough for gravity to start trying to round them out, but not quite big enough for gravity to finish the job. Saturn's moon Hyperion is a perfect real-world example. A heavily cratered, irregular, almost sponge-like body, clearly being squeezed toward a rounder shape by its own gravity, yet still lumpy enough that astronomers describe it, quite literally, as potato-shaped. These worlds are like a video paused in the middle of a transformation, caught between the chaos of an asteroid and the calm uniformity of a true planet, frozen at the exact moment gravity is winning the fight, but hasn't yet declared total victory. Cross that line fully, and something remarkable happens. Every part of the body starts being pulled toward a single shared center, with such overwhelming, even pressure, that the entire object slowly relaxes into a sphere, the same way a soft ball of dough left sitting on a table will slowly spread and settle into a more even shape under its own weight. That crossing point is the formal birth certificate of a planet. Below it, you have a rubble pile pretending to be solid. Above it, you have a true world, round not because anyone designed it that way, but because nothing else was structurally possible anymore. This becomes far easier to visualize once you remember that planets did not begin their lives as cold, solid rock. They were born from violence, heat, and constant collision. Early in the life of any planetary system, countless smaller bodies smash into each other over and over, and every single one of those impacts releases enormous amounts of heat. Add in the crushing pressure of gravity squeezing material inward, along with heat from radioactive decay happening deep underground, and you get a young planet that isn't really solid in any meaningful sense at all. It's closer to an enormous ball of slowly churning, partly molten material, soft enough in its outer layers to genuinely flow the way thick honey flows, just on a much, much slower timescale. A planet that hot and that soft has absolutely no chance of holding on to sharp angles or flat faces. Any lump, any corner, any unevenness gets smoothed out almost immediately. The same way a dropped scoop of warm ice cream doesn't keep its sharp shape for long once it starts to soften, slumping outward into a rounder puddle with every passing minute. And once that material is soft enough to move, gravity has exactly one job, and it does that job with total indifference to the original shape of anything. It pulls every available bit of mass toward the shared center point of the whole object, as directly and efficiently as possible. It doesn't care if that mass started out as a sharp corner, a deep valley, or a flat plane. All of it gets the exact same invitation. Come toward the center. High points get dragged down, low points get filled in. Eventually, every point on the surface ends up sitting at almost exactly the same distance from the center as every other point. And a shape where every point is the same distance from a single center has an official name. It's called a sphere. Roundness, when you really sit with that idea, isn't a sign of an object winning some great cosmic design contest. It's the shape of an object losing a fight. Specifically, it's the shape left behind after every other possible shape. Every bump, peak, ridge, and corner has already been crushed flat by gravity. A planet doesn't choose to be round the way a sculptor chooses a shape for marble. A planet is round because every alternative shape collapsed first, and the sphere is simply the last shape standing, the only shape stable enough to survive its own weight without continuing to deform. Here's a wrinkle worth sitting with, though. Even Earth, sitting comfortably above the hydrostatic threshold for billions of years, is not actually a perfect sphere. If you measured very precisely, you'd find Earth bulges out slightly around its equator and is a little flattened at the poles, making it what scientists call an oblate spheroid rather than a true sphere. The difference is only about 42 kilometers between Earth's equatorial and polar diameters, tiny compared to Earth's overall width of about 12,700 kilometers. But it's not zero, and the reason it's not zero brings in a second force working alongside gravity: spin. Every planet rotates, and that spin creates an outward push strongest at the equator and essentially non-existent at the poles. On Earth, this effect is modest, but that gentle spin is still enough to push the equator outward just a little, and the compromise between those two forces produces exactly that slight bulge. If a slow spinner like Earth still ends up slightly squashed, consider what happens to a planet that spins dramatically faster. Jupiter completes a full rotation in under 10 hours, despite being more than 100 times wider than Earth. All of that speed at Jupiter's equator creates an outward push so strong that Jupiter's shape becomes visibly squashed, distinctly flatter at the poles and wider around the middle. If you look at detailed images of Jupiter, you can genuinely see it with the naked eye. Not a perfect sphere. A sphere being actively deformed by its own speed. Which brings us back, finally, to the cube. The universe doesn't hate cubes. It's not enforcing some preference for curves over corners out of aesthetic taste. The universe simply applies the exact same impartial rule to every single object that exists. Get big enough, and your own gravity will eventually become stronger than whatever internal strength is holding your particular shape together. Cubes don't get singled out for destruction. They just happen to be one of the most extreme, most unstable shapes possible, with mass piled up unevenly at corners and edges in exactly the way gravity finds easiest to exploit first. So in the end, a planet is round, not because nature designed it that way on purpose, and not because round happens to look more pleasing or more natural to our eyes. A planet is round because at planetary scale, every other shape loses an unwinnable fight against its own gravity. Picture every possible shape lined up like competitors, stepping one by one into a ring against an opponent that never gets tired, never makes a mistake, and never stops applying pressure across millions or billions of years. Cubes step in first and lose almost instantly, their corners caving before the fight has barely begun. Pyramids fall next. Jagged, irregular shapes only survive at all because they're too small to be invited into the ring in the first place. But cross that critical threshold in size, gather enough material under your own weight, and only one shape is left standing once gravity has finished its work. Not because the sphere was the best choice all along, simply because the sphere is the only shape that loses to gravity evenly on every side at once, with no remaining weak point left anywhere for gravity to keep pushing against. That's the entire secret. A planet is round because the universe crushes everything else first, and a sphere is simply what remains once the crushing finally stops.